Texas decision makers work to ensure that groundwater is available for beneficial use today and for the next generation. Managing groundwater is the same as managing any budget. A household cannot continuously spend more money than it earns. In the same way, an aquifer cannot continuously give more water than it is taking in.
Accounting for the groundwater budget requires thinking about the water cycle. The water cycle is the continuous movement of water on, above, and below the surface of the earth. Water that enters an aquifer from the surface is called recharge. Recharge includes rainwater that seeps down through the soil to reach the water table. Only a small portion of total precipitation gets down this far. Recharge also includes water draining into the aquifer from streams and lakes. Water that enters from another aquifer is called inflow. Inflows in recharge are comparable to a deposit in a bank account. They add to the overall wealth of an aquifer. Water exiting an aquifer naturally or artificially is called discharge. Examples of naturally occurring discharge are evaporation, groundwater used by plants, springs, leakage into streams or lakes, and leakage from one aquifer to another. The most common discharge from an aquifer by humans is pumping. Discharge is comparable to a withdrawal from a bank account. The amount of water inside an aquifer is called storage. This is comparable to a balance in a bank account. Anytime we pump water from an aquifer, we are drawing down the water level in the aquifer storage. As long as the amount of inflows can replace what we pump, drawdown is temporary and does not affect water availability. When inflows can't keep up with pumping, we're depleting the aquifer. Prolonged pumping in excess of inflows reduces the amount of water in the aquifer, and as a result, pumping becomes more difficult and costly, as water must be lifted from increasing depths.
The Ogallala Aquifer is located in northwest Texas and extends northward into Kansas and Nebraska. Since people began tapping its groundwater, the aquifer has dropped an average of 105 feet. This is an example of an aquifer being steadily depleted by pumping.
Pumping can also impact water that isn't underground. Springs and streams can dry up and no longer sustain wildlife and vegetation. This is what has happened to Big Spring in West Texas. Its spring has long gone dry, but because of its significance to the town, the illusion of a flowing spring is kept up by piping in surface water. Depletion of certain aquifers can cause the land above to sink, making it susceptible to flooding. This sinking, also called subsidence, happens when too much water is removed from an aquifer and void spaces that were once filled with water become empty and collapse due to the weight of the rocks above them. Subsidence is a serious concern along the hurricane-prone Gulf Coast. In parts of East Houston, land elevations have dropped as much as 9 feet since 1900. In addition to pumping, contamination also affects the amount of available groundwater. A variety of activities may introduce contamination into an aquifer, thus requiring costly treatment or abandonment of the water source. Contamination may also result from saltwater movement caused by pumping wells. This is an obvious problem in Texas aquifers that are close to the Gulf of Mexico, but can also impact aquifers that are located far inland. Some of these aquifers contain ancient saltwater trapped deep underground. Drawing down deep aquifers can result in migration of this ancient trapped saltwater into parts of the aquifer that previously contained fresh water, causing a decline in water quality.
To tackle the challenges of water level declines, the state of Texas incorporates the best available scientific methods in groundwater management and planning. A critical component in the state's planning process is the Texas Water Development Board's Groundwater Availability Models program. Groundwater availability models are computer programs that simulate groundwater flow. They account for the amount of water entering as a credit or deposit, the amount of water leaving as a debit or withdrawal, and the amount of water remaining in an aquifer as the balance. These models can be used to predict the impact of large pumping activities on an aquifer. Because groundwater systems are complex, These models require extensive amounts of information to represent the many different physical properties in an aquifer. Scientists from the Texas Water Development Board collect and organize data associated with groundwater and aquifer properties, including groundwater levels, well drilling reports, pumping records, and rock and sediment types. They add it to data on streams, lakes, springs, precipitation, climate, surface water runoff, geologic structure, vegetation maps, root depths, evaporation, and more.
This information is analyzed to quantify aquifer properties and groundwater inflows and outflows. The product of this analysis is a groundwater availability model of an aquifer system. The model is used to answer a series of what-if questions. For instance, what happens to an aquifer if a city increases pumping to satisfy its growing population? How much does it impact the flow from a nearby spring? How much will water levels fall in the aquifer due to increases in pumping or due to the placement of large well fields? The scientists use model simulations and then interpret numerical output from the model to answer these questions. The models generate numbers that require review and interpretation. The scientists check the outputs to ensure that they reflect reality. This is often done by comparing model results against real-world measurements, such as water levels of monitoring wells. Numerical model results may be converted into graphics. For instance, water level predictions can be graphed on charts, plotted on maps, or even animated in 3 dimensions. But most important of all, groundwater availability models are critical scientific tools that state and local authorities and citizens can depend on when making decisions on groundwater use.